Hello, welcome back to the Multimedia Logic SAP-1 based computer series. In this video, we're going to talk about microcode and the way flags are implemented in this computer version. Now, there are some stark similarities between what was done in here and, of course, the bare needle breadboard-based computer. And I wish to go over all of them so that you get to know the computer better. Now, the way microcode is implemented is just as it goes in Benito's breadboard computer series. Basically have a set of words that come outside of some registers. In this case, they are registers instead of EEPROMs. And the way they are controlled is they receive some address, which is the instruction register, and the microcode step, which is determined at the end of this file. You can see that most of the flags are run almost immediately depending on the step and the instruction register value, which is the current instruction. But yet the jump logic is actually determined by a few gates that come outside of here and some of the flags. All registers inside this computer are run with these words. So if you want to have some register put something into another register, by bus interaction, it is required that we use these bits right here to control the buffers and to be sure that the buffers are not being overrun by more than one register. You can see that the flag implementation is also done, and multimedia logic makes it quite simple because the ALU already has both a carry and zero output right in there. Since we're implementing this computer without the need for actual EEPROM memory hexadecimal files, we build everything in an Excel file. So we have each of the instructions that we have available for the computer and the control words required for each microcode step. You can see that in the middle I have this counter, so-called bus check, that ensures that I'm not outputting more than one thing in the bus. Because it can happen that, for example, I have more than one output, and of course that will result in inconsistent bus logic. In real life, that will mean having components try to output different values onto the same wire, which might lead to component damage. Now, this is done for each of the instructions, and you can see that on the right side there are some rows of values. They are hexadecimal values which represent what should be output by each of the microcode registers on each of the microcode steps. Since we have up to 16 possible words, we have two values since our registers are 8-bit base. And whenever we update this spreadsheet to add a new instruction, we will have new rows which can be put into the register memory files that we use in multimedia logic. Well, the way we channel things throughout multimedia logic is by a use of a multiplexer. You see, I'm not very used to the bus logic that multimedia logic has or newer versions. So the way I get to connect outputs and inputs simultaneously by using a bus, well, is by taking advantage of the fact that a multiplexer can have multiple inputs and a single output, which is determined by a channel logic. Now, the way I enroute the channels is by using this little logic, which is basically a counting logic. If we have RAM out, you can see that the result of these logic operations will be a 0. There's no RAM out on the input side of this logic. If we, for example, get A out, which is A register out, it'll fire this bit in our logic, which is the one that gets put in the multiplexer. And that way we count. So for example, if we get instruction register out, you can see that this is wired immediately into this bit, BC1, and the other bits are of course at a 0. So at the end it'll lead to the following number. It'll be 100, which will be put onto all these multiplexers and will result in the routing that we wish. That we want what's in the instruction register going out through the bus onto the registers that it can provide to. And for last, we have the so-called flags. As I told before, the computer does calculate them right away through the ALU, so I don't have to implement any logic to determine if the result of a sum is zero or if it yields a carry. Now, you can see that it's implemented via SR latches with a clock enabled, and you can see that the clock is also inverted. So just as registers, we only update the flip-flop when we have a fallen edge on the clock. That's why I have it inverted, because the normal flip-flop operates on a rising edge. Now, the way they are implemented here is a little bit different from what Malvino's book does and from what Beniter does in his book, in his Redwood computer series, I mean. What happens is that we have a clear flag bit, which is one of the words that we set in the microcode logic, which activates whenever we are using an instruction that is going to affect the ALU, namely LDA, add, and subtract instructions. It is in that time that we are looking for a chance to see if the flip-flop is going to get updated. You can see that the flip-flop will get updated all the time um, when we activate the zero or the carry flag. We're going to see this exact implementation for the top one, but we want to be sure that we have a chance to update it for real when we are doing those specific instructions. So that's why we have this clear flag. We of course prevent both set and reset being enabled, which is of course a not valid an invalid condition for this flip-flop, by using this AND gate and this inverter right here. And with this, we can ensure that even though we have a zero in here in the ALU, that we are able to clear the flag before that calculation by running it through this logic. So if our clear flag, if our clear word is set, it's gonna null this AND, and we are not gonna have a way to set the flip-flop in the case of a zero flag. You can see it's the exact same implementation for the carry flag, and that's the way it goes regarding the way the flags are updated. So let's try to understand it more by an example. Let's take a look at the jump instruction. You can see that the jump instruction is quite clear. It doesn't require many microcode steps. What we do is simply make a fetch cycle, which is getting what's on the RAM and putting it in the instruction register. And then we make the following. We get what's on the instruction register, and we put it on the program counter. Because we are jumping anyway, there's no need to increase the program counter. There's no need to go to the next instruction. We just get what's in here on the instruction register and put it in the program counter, which is basically updating the program counter so that the next instruction is the jump. Um, you can see that the microcode I implemented does the program counter update at the end of the instruction. So we have program out, memory in, which is basically prefetching the next instruction, so that when we load the next instruction, we can, of course, do RAM out and instruction register in. Now, the difference between this is and the upcoming instructions, jump if zero and jump if carry, is of course that the jump word um, is not determined directly by the microcode. There's actually some logic inside it. So I have instruction out, but it doesn't mean that I have to output the required, let's say, address. It doesn't have to be put in the instruction register right away. I don't have to make a jump right away. And the logic works like this. I get the most significant bits out of my instruction register, which are basically the current instruction. It can be a jump carry or a jump zero, and I determine whether I am on step 3 of those. That's why I have this MC2, MC3, and the AND gate in here. I have to determine if I am either in a jump carry or jump zero instruction, which I do by using these multiple input NAND AND gates and this NOT gate, because that helps me determine whether I am on instruction number 7 or instruction number 8. What comes next for each of those instructions is, of course, determining if I am on the valid step, if I am on the valid instruction, on the actual instruction that will require a jump, and if the flag is set. So I have this triple AND. One of them refers to the instruction, if it is instruction number 7 or instruction number 8. The other one refers to the microcode step. I have to be on step 3 because that's where I get the instruction out. That's where I get the destination in the bus, and then I determine if I wish to put it or not. And the last bit is of course the flag that I determined previously, either the zero flag or the carry flag. And that goes into this or that enables the jump word. Now you can see that all three have an OR because there are three conditions in which the jump can be enabled. Either a unconditional jump, which is instruction number 6, um, and a zero or carry jump, which is determined by this logic in here. And that's the microcode and jump instruction for this multimedia logic implementation. Thank you for your time.